Tim. Let's hear it.
All right, well, my name is Tim Cannon. I'm the group leader for this first experiment for Group 1, which is the Clapeyron experiment. I just am I pronouncing that correctly? Yeah. All right, perfect. We can go next. So we've got a few objectives for this lab, as with every lab. Mostly we're going to be trying to find the latent heat of vaporization of water. We're going to do this using 3 different methods, each of which use an increasingly better approximation of the derivative of the graph, which I'll show you in a little bit. We're also going to find this over a range of temperatures and pressures. We're also going to compare the measured data to the theoretical data in the steam tables, which I'm sure we all remember enjoying from thermodynamics. And then finally, we're going to compare the results when we use boiling beads, which are essentially just little glass balls in the water, compared without boiling beads. So here is our apparatus. This is going to be the main part right here, our flask, which is going to have some water, and also this rubber stopper up top, which is going to house our thermocouple, the pressure, the device, the pressure transducer, and all the ways we're going to control the experiment. Got our hot plate. Obviously, we're going to heat up the water with that. And so this thermocouple here, it's important to be sure that is submerged just into the water. We don't want to be picking up readings from the glass or the beads or anything else. So that's going to be a way that you can have uncertainty. We want to keep that as minimal as possible. And the other important section is over here. So our air bleed. Essentially in this experiment, we're going to be increasing the pressure inside of here, and we don't want it to reach over 1 atmosphere. Or else bad things could happen. So once we start getting close, we're going to open that up just to be sure we don't cause any damage to ourselves or the experiment. And then right over here, well, this whole rig basically is how we're going to control the pressure inside of the flask. Go to the next one. So this experiment, we're dealing with enthalpy. Tripp talked about it a little bit a second ago, and I think we all remember with thermodynamics. It's essentially the internal energy plus PV of the fluid. And so there's 2 ways you can do. Well, I guess in this experiment we're showing how you can measure data and then use these equations in order to find the thermodynamic properties of the fluid. And so in general, you can do this, looking at the difference between 2 different phases or the changes within a single phase of the fluid. But for this one, we're using the difference of properties between phases. And those 2 phases for us are going to be the saturated liquid and the saturated gas phase. So this Clapeyron equation is derived from the current cycle where we heat up from the saturated liquid until we get to the gas. So, which is essentially evaporation or vaporization. And so we get this equation. Here's the derivative I was talking about earlier. It's the change in pressure with respect to temperature. And so we're going to substitute in for V here with the ideal gas equations in order to find this. We're going to essentially be solving dP sat dt equals HFG P sat over T squared R. So that's going to be the final Clapeyron equation that we're solving in this experiment. You got the next one? So here is our expected results. Hopefully, our data is going to show a line very similar to this. This is going to be our raw data, pressure and temperature that we're going to record on the computer. And right here, this is the steam table graph. And so the slope, the derivative I was talking about is going to be the slope of this graph. And so each of the 3 methods, we're going to more closely approximate that slope and hopefully improve our results. You go to the next slide. So here are the other expected results of finding the latent heat of vaporization. So here's that equation, the Clapeyron equation, rearranged to be solving for the latent heat of vaporization. And I picked 3 arbitrary temperatures, which correlate to pressures, to solve for. And so you can see over here in this graph, off to the right, or not graph, the table, I guess. Those are the expected results versus these actual results. And we see a little bit of variance. This is likely due to either the ideal gas substitutions we made, because obviously nothing's really an ideal gas, or it could be from the Carnot cycle, since you can't physically have a Carnot cycle, which is where we're deriving the equation from, or also from the inaccuracy of the slope, because I found it using approximation rather than the exact slope there. Other than that, like I said, we could have uncertainty in the temperature readings. Obviously, you can also have uncertainty in the pressure transducer, just depending on how it's manufactured. From instrumentation, if we've taken that yet, we understand those ideas. You could also have issues with the actual amount of pressure built up in the flask. Because it's a rubber stopper, we're not using it really tightly sealed. There could be some leakages there and everything like that. So those are going to be the main sources of uncertainty in this experiment. Are there any questions or anything? Yeah.
For the pressure transducer, does the computer automatically convert the voltages into pressures, or do we manually have to do that, or do you know?
I actually do not know. It's a good question, which I think, Addison, you can correct me here, I think it's going to automatically convert them. At least that's what it has done for temperature, which we saw in the practice experiment. So
okay,
that's my assumption there.
That should be a problem. Pressure per side.
Okay.
So then that's another source of uncertainty potentially, is if it converts them.
Right.
That conversion factor. Anyone else?
I just have a quick question.
Absolutely.
Is 10, what is that?
That's the computer.
Okay. It's a smiley face, so it's just like, oh, it's
It's like a happy
smiley.
computer.
Okay, got it.
So yeah, I mean, you see the thermocouple and the pressure transducer, and we reported on there. We're going to save that, and then we're going to make our plots and have a good time with all the analysis. Anyone else? All right.
All right. Thank you so much, Tim. I'm glad I can finally pronounce that